There, finally it told me we were recording. Don't know why that takes so long sometimes. All right, so we're going to go on to 4.2. And actually, before we do that, I just want to make sure how many people we got here. 21. All right, cool. Okay. So we're going to, so last class we talked about regression. I'm going to go ahead and continue with, oh, that's the wrong class. You're glad you're not in my other class. They had their first test yesterday. So, although it was easier than your test, so maybe you would have liked to have been it. Okay, so after you do correlation, and you decide you think it's a good idea, the next thing you want to do is regression. And so I'm going to go with the one that we've already worked out here. Okay. So, oh, this one's already, actually, this has got more than we bargained for. No, yeah. Okay. So the idea here is you can add what we call a regression line onto your graph here, okay? Now you'll notice the points, some of the points that are right on the line, like this point here is right on the line, and that point at the end is on the line. The rest of these points are off, okay? Now the question is, which is the best line you can draw? So there's three lines. You could draw the draw a regression line so that you minimize the vertical distance. So this distance here to the line is what we would call the residual, or this distance from here to the line in the vertical direction. We could also do it in the horizontal direction, this distance here, or this distance here, or we could do it with so that it makes a right angle, draw a line so that it makes a right angle with the line. And that's what we call the orthogonal distance. So the question is, which is the best distance? And if I go back to my notes here, the least squares regression line finds the minimum vertical distance. Oh, I guess I should put vertical in there. Vertical distance to the line. So the formulas that we're going to use for that are, so basically the equation for the least squares regression line, you can think as y equals mx plus b. Sometimes they put a little hat on top of there. So y equals, now in the formula sheet, it's also written as y hat equals b1x plus b0, but most of my students are more familiar with this format here, y equals mx plus b. And so just realize that this formula here is the same formula as mx plus b. So so there's two equations that we need to use here. So the slope is the m in the equation there is going to be your correlation coefficient times the standard deviation of y divided by your standard deviation of x. And your y-intercept, which is b, or in this case, it's a b0, is y bar minus m times x bar. So so the idea here is, let's go ahead and find out what the equation of this line is. And so let me pull up these two equations here. Whoops, didn't mean to do that. Copy that. So these are the two equations that we're going to need. Okay. Okay. So your slope is going to be your correlation coefficient. So yesterday we talked about this problem here, club head speed and distance. And so In this case, we got a correlation coefficient of 0.938696, and we found out the standard deviation already were those two values there. So when I do my slope m, it equals simply the correlation coefficient, which was 0.938696, times the standard deviation of y, which is your distance, times your standard deviation of x. That works out to be 16.67857. Okay. Now your y-intercept, which we call b, that's simply y bar minus m times x bar. Okay. So y bar is going to be your mean for your y distance times the slope that we just found, which is 16, subtract. Subtract the slope that we just found times your x bar, which is 101.875. Okay. Oh, wait, what did something wrong? Y bar minus m times x bar. Why is that? That doesn't look right to me. I can cheat with this.
Do you need to put the y minus the slope in parentheses?
That shouldn't matter. Display the equation. Oh, my slope's off. Why does my slope get off?
I think.
Okay, that's.
Don't you need to do the standard deviation of y divided by the standard deviation of x instead of multiplying them?
Did I multiply them? Ah, yeah. There we go. That's why. I knew that was wrong. There we go. Now I get the right answer. So make sure you plug your formula in correctly. Yeah. Yes, that's exactly what it was. Yeah. Okay. So 3.1661 minus 55.797. So as we're writing this down, y equals 3.166102 if I'm going all my decimals, x, and then I need to add my negative 55.7966. Okay. And as you can see, there is a way in Excel, but you can't use Excel on the test. I was trying to avoid that, but I knew my answer looked wrong and I couldn't figure out why. But yeah, so that's the same equation that they got there. So, so that is the least squares, ordinary least squares. A lot of times we'll abbreviate that as OLS, regression equation. So these calculations aren't too bad. Basically on the test, those are the sorts of things that I'm looking for. Let's see here. So remember to keep the predictions in range. Now, so here's the thing. If I were, so you can see here, my club head speed is always from about 99 miles to 106. I could probably deviate out there a little bit, 98 to 107, and it probably would be okay. But if I go much farther out, now let me ask you a question. Should I pick on somebody or should I let you guys? Here, I'll let you guys choose if you want to answer this. According to this equation here, how far would the ball go if I hit the ball 0 miles per hour?
Would it be negative 55?
Yeah, it would go backwards negative 50, almost 56 yards, right? Does that make sense?
No.
No,
Really.
you would expect it to go 0. And so that kind of shows you, if you go really far outside the range, that prediction outside the range is risky, okay? So what probably happens is there's probably a curve somewhere in here that's eventually going to catch up with you. Here, I'm going to make that a little better there, okay? So yeah, so this equation doesn't make sense if you hit it 0 miles per hour. It's going to go backwards according to this. So it's good from 99 to 105, basically. That's what we've got here. You can go a little bit outside that, but if you go too far outside that, it could curve either before, you know, linear is good for this range. It's not good for outside the range. Does that make sense?
What's this really showing you then?
So the idea here is you can predict. So for example, I don't have a value here. So how would you predict how the distance if I shot the ball at 103 miles per hour?
Well, you'd go to the 103 on the line and then find where it intercepts on the line.
Yeah, so that's one way. That's not a very accurate way to do it, right? Well, how could we?
You could also plug it in.
Yeah, you can plug it in here. So tell me what to type here, and we'll plug it in.
You take your equation 3.166102 times 103.
103, and then we're gonna add the y-intercept on here. So we would predict that it would go about 270.3 yards, which when we look at our line here, yeah, it's about right on the 270 line there. So that's pretty good. Now, another thing, let's see, do we not teach you this? I think we're gonna get done early today. Trying to remember. Oh, that's what I wanted to do. That's actually in 4.3. Okay, well, we're going to get done early today because I think this is fairly easy. Although maybe I should wonder if we can come up with, well, that's really for the next lecture. I kind of want to do this again. Well, we'll do it again, but let's see. I want to make sure I've covered everything here before we move on. Okay. Actually, let's talk a little bit more about residuals, okay? So the idea, well, I really want to do this. In 4.3, we're going to talk about the R-squared value. We're going to cover 4.3 today, I think, too. R-squared is called the coefficient of the determination, and it's the square of the correlation coefficient. So this value is always between 0 and 1. And the idea is it tells you the percent of variation explained by the model. Closer to 1 is better. So let me go back here as we look at this, okay? So the funny thing is, I don't know anybody that calls this the coefficient of determination, but if you take your correlation coefficient, which we found yesterday, and you square it, okay, this tells you how good your model is. So 88% of the variation explained by this model is simply based on how fast you hit the ball, which means that about 12% is unexplained. Okay, so we probably have some golfers in our class. Okay, if 88% of the distance can be explained simply by how fast you hit your club head speed, what are some other things that would affect the distance?
Well, you could your driver size, your the type of ball you're using, because there's higher quality and lower quality balls.
Okay, so we're assuming that we're hitting it with the same driver in this thing. What else would be?
The way you hit the ball.
So I heard the way you hit the ball.
Meaning like your backswing, like if you hit a slice or a hook, or depending on how you hit it, if it's straight or not.
Okay. There was a female voice that I barely heard, but I didn't hear what she said.
It's wind.
Wind. Wind would be a good one. Okay, maybe it says that there's no wind, but you know, it's hard to hit a ball with, you know, there's probably a little tiny gust of wind that might either push it back towards you or push it farther. That could be something else. What else might help or hurt? Maybe you hit a pebble and it bounces farther because you hit a pebble, or it bounces back because you hit a pebble. Maybe if you hit a wet spot, that might help it go farther. Dry spot, maybe not so far. Things like that. So the idea here is the R-squared value can give you a good idea on how well this, how good your model is. So closer to 100%, it explains it really well. Closer to 0, it's not a very good model. So you can use the R-squared value to determine how good your ordinary least squares regression equation is.
Can you go back to the R-square definition real quick?
Okay. So the R-squared definition is it's the square of your correlation coefficient. This tells you the percent of variation explained by the model. Closer to 1 is better. Okay.
Thank you. Thank you.
Yeah, no problem. All right. So now, actually, I remembered there was one more thing I wanted to do. Okay. So we've got, you can see here, these are our calculations that we used for our for the correlation coefficient. What I would like to do is I'm going to copy this information. Oh, I've already got it here. That's interesting. Okay, so here's what I'm going to do. Okay. Now let's talk a little bit about residuals. Let me go back to 4.2. Okay. Residuals also can help us see how well the line fits, and we're going to compare two different methods. Okay. Now the residual is basically the actual minus the predicted, and using each equation, and I'm going to use a different equation, and we're going to compare these. Then we're going to square the residual, and we're going to sum them and see which method is better. Least squares method should be better, and lower sums indicate a better model. Okay. All right. So let me go back to here. Okay. Now, okay, so the ordinary least squares method gives us this equation here. Now, let me go back to my picture for just a minute here, okay? You can see that there's these 2 points here. There's the one at 99, which happens to be this point here. So at 99 miles, we hit it miles per hour, we hit it 258 yards. And you can also see this point here, which is also on the line, which is at 105. So at 105, it went about 277 yards. So we've got these 2 points here, okay? Now, if I have 2 points in a line, I can come up with a different equation rather than use the ordinary least squares equation, okay? So if I have these 2 yellow points here, maybe I'll go over here. Nope, I'll go here. So this point here and this point here. So for those of you who have had math 1010 or even high school math, if I have 2 points, I should be able to find the equation of a line. Do you guys remember how to do that?
X minus y1 and, or x2 minus x1 and y2 minus y1.
So that's the slope, right? So your slope is, what'd you say? Or was that not for me? Okay, so I don't know, I don't recognize your voices here. Somebody gave me this slope equation here. That's definitely going to help me find the slope between these two lines. And then how would I find the actual equation?
Once you find the slope, then you would use y equals mx plus b and plug in one of those points, the x for x and the y for y. So then solve it to find b.
Oh, okay. So you can do that. There's also another equation. So since I don't have the y-intercept, I could just pick one of the points.
Isn't
you
it
guys
y?
remember the slope-intercept equation?
Yeah, it's equals y1 minus y2. Oh, y1 minus y2 equals x1 minus x2 times something.
Yeah,
Is that right?
you're giving me the slope equation again. Y minus y1 equals m times x minus x1.
That's what I was trying to say.
Yeah, that's what we're looking for. Okay. All right. So if we find the slope, so if I take y2, so let's take 277 minus 258. That's my numerator. And then if I take 99 minus, oh, I started with 277, didn't I? Yeah, I did. 105 minus 99. Okay. Oops, I'm supposed to say minus, not equals. Minus. Okay. So this is going to give me a slope equal to the numerator divided by the denominator. Okay, which is 3.1667. So you can see that's really similar. Really similar to the slope we got the first time, right? And then I can pick either point here. I'll pick 27. So if I take y minus y1, so I'll pick this point here. I could pick either point. So 277 equals the slope that we just found, which is this 3.1666666 x times x minus x1, which is 105. Okay, and then if I wanted to solve this for y, I'm just going to add 277 to both sides. So this becomes y equals 3.16666x times x minus 105, and then I'm going to add 277, which I think is this equation here, if I distribute everything. Except for I put a plus there, that was supposed to be a minus. Okay, so if I want to simplify that further, I'm going to get y equals 3.16666x minus, and actually let me do it this way. If I take this times negative 105, and if I add 277, that's going to give me negative 55.5. So that's how I got this other equation. Okay. So what we're going to do is we're going to compare the ordinary least squares method with the method that you guys are used to, because, you know, I was looking at Anna Bennell and she was saying, you know what, I don't believe that ordinary least squares method. I could just tell by looking in her eyes she was concerned. Okay, so I'm going to prove to you guys that the ordinary least squares method, because what I'm going to do is I'm going to find the sum of the squared residuals, and I'm going to get a smaller sum using the ordinary least squares method than using the method that you guys are used to. Okay. All right, so let's pick on oh, whose turn? Who haven't I picked on in a while? Jed, it must be your turn. Jed, can you help me plug in? Okay, so remember, the ordinary least squares regression method can be used for prediction. If I hit it 100 miles an hour, it went 257 yards. What would my ordinary least squares predict I would have gone? Can you tell me how to do that?
Honestly, I'm trying to catch up in the textbook right now just because I feel like for 5 minutes I got a little lost, and so I definitely cannot tell you that.
Okay, all I want you to do is I want you to plug 100 into this equation, and we're going to see what the difference is between the 257 and if I plug 100 into this equation.
So you would plug 100 into the x, is what you're saying?
Right.
Okay, so it would just be the 3.1661 times 100 minus 55.79. So then that would be 316.6 minus 50, right?
Yeah, except for I put plus and I was supposed to put a minus like you said. Okay. Okay. So I went 257 yards. According to my prediction line, I should have gone 260.8. And so if I take the actual minus the predicted, then I'm off by about 3.82 yards. Okay. Now I'm going to square that result. And that's going to give me 14.5924. Okay.
And is that the coefficient of determination?
No.
Okay.
No, this is the residuals. We're just trying to find the residuals. So this right here, this column here is the residual. So you can think of the residual as how much your prediction is off. Okay.
Okay, cool.
So in this first case, we're off by 3.8 yards. Okay.
So I have a question. Does it matter if we subtract the actual from the predicted or the predicted from the actual if we're just going to square it?
It doesn't matter
Okay.
if we're going to square it because the square is going to get rid of the negative sign.
That's what I was thinking. I just wanted to make sure that we weren't going to use the residual for something else where it would matter.
So let me just say this, okay? I know this is a little bit weird, and this is going to come back probably the last week of class, and we're going to talk about this same thing. And so this will come back to haunt you if you don't learn it today. So anyway, I'm going to go ahead. I'm going to copy this down for each of these 7 points or whatever we've got. So you can see we're generally off by about 2 yards. This one's almost on the money. That was off by 0.3 yards. So these are all pretty close, okay?
What's the squared result showing you?
The squared result, basically, we're just squaring each of our residuals.
For what purpose?
See, the purpose is I don't want, if I add these up, the negatives are going to subtract from the positives, and I don't want to, that might add up to 0, I think, or pretty close to 0. I want to be able to basically get rid of the negatives, and so I'm going to square those so that I don't lose that value. Think of it as the absolute value that these are off, but I don't want to use absolute value. I'm going to square it. So in chapter 14, we're going to do this again. There's a mathematical reason why we want to square it instead of use the absolute value, and we'll learn it again in chapter 14. So I'm just kind of preparing you for chapter 14. So we're going to need to find the squared residual result. And so at any rate, I've got 49.85. So I know that's not a very nice answer, but I don't want to get into a lot of statistical theory. I'm just going to say, just trust me for this. Okay. We need to do this, and there's a mathematical reason, and I don't want to confuse you with that for now. Okay, so we're going to use this result again in chapter 14. But the result is I've got my squared result, the sum of all these numbers is 49.85. So smallers is better. Okay. Now we're going to do this same thing, what we just did here, and we're going to use the other method that we're used to from college algebra. So let's pick on Caitlin. Caitlin, can you help me do the same thing? We're going to use this equation this time to predict how far the ball should have gone if I hit it 100 miles an hour.
Yeah, so you're going to take the 3.667 and times it by 100 and then subtract your 55.5.
Okay. Something seems wrong here. It seems like it went too far. 3.6667 times 100 minus 55.5.
Be 3.1667.
Ah, okay. Thank you. Because I was like, there. I didn't put a 1 here. That should be a 1 there. That's better. Okay. So we're going to do the actual. It went 257 yards. We're going to do subtract our prediction. So you can see this one was off by a little bit more. Okay. I'm also going to square that result. Okay. All right. So if we compare this one, this has a better residual than this one. Now I'm going to repeat this for all of these. You'll notice here that in some cases, like this case here, this was a better prediction. This one was off only 1.6 yards, where it was off 2 yards here. So sometimes this is better, sometimes it's worse, okay? And so as we look at this right here, you can see my sum works out to be 50. 49 is better than 50, and so therefore, because I have a smaller residual sum, the ordinary least squares method is better. Okay? So, any questions on that?
Do you want us to do both methods each time and then show which one's better, or is the ordinary least squares method always better?
Ordinary least squares method is always better. Okay. So I only did this to show you that it was better. Okay. This is really all you need to know. Now, so it's kind of funny that they talk about the residuals in 4.2. 4.2 is actually a fairly short section. The main thing I want you to take away from that is, can you find the slope and you can find the intercept with these two equations? They introduce you to residuals, but really 4.3 is where we start getting into that better. In fact, if I were writing the book, I would have put this in 4.2, and then I would have put the residuals with the residual plots. The idea here is, now we're going to talk about residual plots, okay? So we're into 4.3 now. So we're going to look for patterns to see if linear is a good model. And the idea here is, it's a good model if you have a null, if you see no pattern, also known as a null plot. You want to see a null plot. Want to see a null plot. And so if there is a pattern, then what that's going to tell you is linear correlation is not a good idea, okay? And so, so the idea here is I'm going to take the club head speed. Oh, this is when I really wish that we could use Excel, because this is where this is going to come in helpful. And I'm going to plot the residual, okay? So I'm going to do, remember, I'm using the X data and then I'm plotting the residual data. And I'm going to cheat and I'm going to use the Excel plot here, okay? Now, as we look at this plot here, okay, there's no real pattern to this data, okay? So here's, okay, so the idea here is you want to see a null plot. There's no pattern to this data that you can think of. Remember, we talked about the hamburger, the hot dog, the banana, okay? So the types of patterns that you don't want to see, if I go back to 4.3, don't want to see parabolas or curves for the residual plot. Okay. If you see these, then that means linear correlation is not a good idea. Okay. The nice thing about so we're using the golf club example once again. I don't see any parabola. Sometimes, and in fact, when I say parabolas, I should say, what is the word that they use? A cone. I'm trying to remember what the name of the word is that they use. But anyway, so let me go back to another example. Okay, obviously parabola is not a good idea on this one because that's not a straight line. But this is kind of interesting here, okay? Move out of the way for a minute, okay? Now, this is an example of baking a cake, and we're trying to determine if linear regression is a good idea. Now, the interesting thing about this here is you can see this looks like a straight line, okay? I've actually got a different type of regression in here. So if I were to plot these as a scatter plot, you can see here this looks like it's a straight line. Okay, this is the regression equation that we would use, and so if I compare the temperature to the predicted value, I'm going to have a very nice looking residual here. These are all really small residuals. Whoops. These are all very close to zero. If I do my residuals squared, I'm going to take this, I'm going to square it. So this looks like it's really nice. And I'm going to get a nice small sum. In fact, that sum is less than 1. So you might say, gosh, a straight line looks like a really good idea here. However, when I plot, in this case, the time versus the residuals, okay, that actually gives me this graph down here. Okay, does this graph look like a null plot?
I mean, you couldn't draw a straight line through anything.
But can you draw a curved line?
Yes.
Yes. The word I was thinking of was megaphone. Megaphone, okay? A lot of times so this one's interesting in that it's kind of a downward facing parabola here. So this tells me linear correlation is not a good idea. Even though, so this is kind of funny. So the idea here is we're looking for these kinds of patterns, okay? A lot of times you'll see a megaphone pattern. Typically, so this is the regression equation here. If I see something like this that says, yeah, you shouldn't use linear regression, You'll notice I tried some other type. The one of the nice things about Excel is you can try linear regression, you can try logarithmic regression, you can see how these match. So that doesn't seem like it matches the points very well. You can try polynomial regression, and that actually looks like it fits really well. I can add the equation and the R-squared value on the chart. In fact, you can see here, as I compare the R-squared values, if I go back to linear here, linear does look, if I look at the R-squared value, it does look like it's really a good fit. The polynomial is actually even better, 0.999. The interesting thing about this is I could try to do a residual thing with this equation here. Now, normally, all I want you to know is there are other types of regression. I'm not going to ask you to do a polynomial regression like this, but Excel can do it. And all I really want you to take away from is when you're plotting these points, this does not look like a hamburger or a null plot, and so therefore this line, you probably shouldn't use it. Maybe you should pick a different type of regression, such as polynomial regression. Does that make sense? Okay. Most of your homework for this is going to be. Say it again.
I have a question. So you said we don't want curves or parabolas because if there is one, you don't want to use linear correlation. But if you want no pattern because that would imply that there's linear correlation.
We want no pattern because the idea here is we don't want to have any sort of, so a null plot like we got here, there's no real pattern going on here. A null plot indicates that there's no error in a certain direction. Okay, this indicates our error is evenly distributed for all of the points. Whereas here, the error is not constant. So this tells us we do not have constant error variance. And so that's why we shouldn't use linear, even though this looks like a pretty straight line. In fact, it looks like a really straight line. Linear correlation isn't recommended. You should use some sort of other method. So your homework in chapter 4.3, section 4.3 is going to be looking at residual plots and saying, is it a null plot like this? Okay, if this is the case, yes, linear regression is a good idea. If you get a null plot like this, no, linear regression is not a good idea. You should not use that equation there. Questions? Okay. All righty then. Well, I think I covered both of those sections pretty well. Oh, I guess here's one more thing. Outliers and influential observations. Oh, let me mention this one other thing. In fact, let me go back to 4.2 for a minute. We do need to be careful here when we're talking about outliers. Now, whenever we're doing ordinary least squares regression, we assume no outliers. Okay. Now, if I do have an outlier, like let's say that I hit it 105 yards, and instead of going 277 yards, it went 377 yards. Just something weird happened. Now you can see clearly that's this point right here. You can see how I don't have the original equation. I guess I do over here. So the original equation, sorry, it's right here, 3.1661. When I put the outlier in here, 377 instead of 277, you can see that that the equation changes pretty drastically, and this the line shifts to compensate for that point. So so we need to be careful, because this point now, 377, is what we would call an influential point. It's going to pull the line towards itself. Now, we don't necessarily have to. Let me put this back to 277, okay? Now that's also an outlier. Now, what if I did, instead of 105, I went 120 miles an hour. So this one is going to be, once again, you can see this, but let's move this to, in fact, let's move it to 150 miles an hour. And then this is going to be 350. Okay. Now, the interesting thing about this is, let me see if I can put it more in line. Let's go with 300. Okay. So once again, you can see that both the speed, 150, is an outlier, and you can also see that the distance, 300, is also an outlier. Maybe if I should go to 280. Oh. Well, 300 was pretty good, I guess. The slope didn't change all that much. So sometimes, let me see if I can give you a better example here, where I can just fake my data a little bit. Okay, so if I've got, I've got my scatter plot here, and I'm going to just draw some little circles here to represent my data. Okay, you might have something that's perfectly in line with your data. Okay, you should be able to recognize that this is both an outlier and an influential point. Okay. Now, if maybe I'll pick a different color here, such as red. If I had something that's way out here, this is also an outlier. It would also be an influential point. The problem with this red dot here is it's going to pull my regression line towards it. Whereas if I stick with this point, so pretend this isn't here anymore. This other point here is probably going to be more in line with the data. Okay. So whenever we're doing regression, we need to be careful about outliers and influential points, because these can really affect the trajectory of your regression line. So there's a figure on page 231 in your book. It has 3 outliers that seem to cancel each other out. And so also there's a picture in your book, I'll let you just look at that, that shows with and without Tiger Woods. Tiger can drive the ball farther than anybody, and so we need to determine if he should remain in the data set. We shouldn't just throw him out because he really does hit the ball that far, but just need to be careful about that sort of thing. So, all right. I'm going to end there. Quiz tomorrow will be on both sections 4.2 and 4.3. Those go together. And any questions before I let you go?
Can you post the Word docs from yesterday's class and today's class?
Oh, I forgot to do that. Yes, I can do that.
Thank you.
Any other questions? Okay, I'll let you guys go. See you all tomorrow.
Thank you.
Thank you.
Thank you.